Let's begin. We are doing empty evaluation, and we just introduce the requirements there. The first requirement is operational evaluation, where the empty system is compared for their cost, efficiency, and so on. Okay, these are operational requirements. Then typological evaluation is most difficult, which asks, do you think machine translation system A covers more language phenomena than B? Okay, so that's a very difficult question to answer. And declarative evaluation is how does quality of output of a system fare with respect to that of B? So this is where we have comparison-based evaluation. Okay, we have reference translations, and the references are compared, and from there we give judgment about which system is better. So this is done with respect to the blue score by making use of blue score. Then Then we understood that there are two very important parameters. The first is called adequacy, which is for capturing of the meaning of the source sentence faithfully in the target language sentence. That's called adequacy. And fluency is with respect to how good is the output with respect to its syntax and formation. Okay, so to give an example of that, I know the boy who lives in Delhi. If the Hindi translation is मैं उस लड़के को जानता हूँ जो दिल्ली रहता है, so that's an adequate translation, but slightly less fluent in the sense that Hindi native speakers don't use such a construction. They would use मैं उस दिल्ली वाले लड़के को जानता हूँ. So fluency also refers to the idiomaticity or naturalness in the output. Okay, the output now the demand on the output can be very stringent in the sense that the output may have to preserve the pragmatics, the politeness, the sentiment, emotion in the source language. All this should be preserved properly. Even the manner of speech. Okay, so if the source language manner of speech is like the text between two friends, for example, where lots of slangs can be used. And if the target language does not preserve that slangness, but produces a very formal output, then then there is lack of fluency, not adequacy. Meaning is preserved. So this is how the machine translation evaluation proceeds. There are lots of subtleties and complexities involved in evaluation. Now, so this is the form-content dichotomy. Form refers to fluency, content refers to adequacy. Now, we have looked at all this. Let me remind you of this 5-point scale for adequacy and fluency, which human beings assign. So bad is 1, mediocre is 2, 3 is good, 4 is very good, and 5 is excellent. Now, whenever we have human performed evaluation, then we insist that at least 60% of the test sentences should be in the level 3, 4, and 5. That's a very standard requirement. And human evaluators are very sensitive to morphological variation, function words. They do not tolerate those errors, which again, I mentioned the other day. Now let's look at BLUE, okay, which is one of the pillars of machine translation evaluation. And it introduced the notion of comparing the machine output with a reference output, okay, in terms of n graphs, n going from 1 to 4. Now, so finally, we would like to match any kind of human performance, any metric that we propose, whatever be the field, should correlate well with human beings' judgment, okay? Now, Blue has been very successful in terms of its high correlation with human judgment. Okay, let's look at the construction of Blue, how it is gradually developed. Okay, so these are the basics. There is what is called candidate translation coming from the machine translation output. This is called candidate translation. And reference translation is the perfect translation by human. Perfect in code because even human beings make bad translation. Okay, there are umpteen number of examples where the reference translation itself is of bad quality. Then what can you compare really? So candidate translation and reference translation, these are the two terms. So goal of Blue is to correlate well with human judgment. So let's go through the formulation of Blue step by step. Um, Typically, in reference, we have try to have more than one translation. Okay, because the same sentence can be translated in multiple ways in the target language. And if it is Indian language, you have a lot of freedom with respect to word order at least. Okay, मैंने अभी खाना खाया, अभी मैंने खाना खाया. Okay, खाना मैंने अभी खाया. All these variations are possible. So, and also you can have synonyms. मैंने अभी खाना खाया and मैंने अभी भोजन किया, for example. Two different sentences. So, if the candidate one coming from a machine translation system is मैंने अब खाना खाया, then let's note how the n-gram precision is computed. First, we uh, think about unigram precision. How many words match with the reference translation? How many words does the candidate match the reference translation? Words are unigram. So मैंने खाना खाया, these three words match with the reference translation. मैंने अभी खाना खाया. So the precision, unigram precision is 3/4, which is 0.75. Similarly, the bigram precision is 1/3. That's because uh, मैंने अब doesn't match anything in the reference. Ab khana doesn't match anything. Khana khaya matches. So one bigram out of three matches. So 1/3 is the bigram precision. What about trigram precision? Do you have any match here? Trigram means consecutive three words. So here, do you see any match? Hmm? There is no match at all, right? And that is happening because of the difference between abhi and ob. So because there is a unigram mismatch, a lot of things in the neighborhood of that word uh, give rise to mismatch. Okay, and there is a neighborhood, okay, which depends on n, the n-gram which will match. So unigram mismatch can have percolating effect for higher n-gram. In bigrams, trigrams, everywhere it can have effect. Okay, so unigram matching is very important. Unigram matching corresponds to vocabulary match. The words in the translation should be captured. The translation of cat should be Billy, okay, not Gaia, for example. So unigram mismatch percolates into higher n-gram mismatches. So that has to be remembered. So whenever we build translation systems, we try to make sure that the vocabulary match is good, first and foremost. Hmm? And as you know, since there is synonyms possible, synonyms can lead to unigram mismatch. So there is a measure called meteor, 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 which tries to accommodate the synonym match also. Okay? Otherwise, if synonyms are there and there is unigram mismatch due to synonyms, then in spite of the translation being good, you'll get low score. Okay. And then we have another candidate output. मैंने अभी lunch ate. So this is a bad translation. Adequacy wise fine. Okay, because the meaning is conveyed, but fluency is bad here. And here we see that that the unigram precision is 2/4, okay, which is 0.5, and bigram mismatch, bigram precision will be 1/3, which is 0.33. Okay, so then I can say that since the unigram precision is 0.5 and unigram precision in the previous case was 0.75. We would like to say that this first translation is better than the second translation. Okay, so we are beginning to see the emergence of a metric which is closer to reality, right? Where better translation is getting better score. So let's summarize what we did so far. We calculated unigram precision, which is number of unigrams matched divided by number of words in the reference in the candidate translation. Okay, and we compute unigram precision, bigram precision, then trigram, and then quadrigram. Typically, we do not go beyond 4. Okay? So unigram, bigram, trigram, and quadrigram. Now, the metric can be fooled. Okay. So let's take this candidate translation. I will be very thankful to you is the source sentence. The reference translation is आपकी बड़ी मेहरबानी होगी. आपकी बड़ी मेहरबानी होगी. Candidate 1 is आप बड़ी मेहरबानी होगी. So here the matching unigram is 3. Bari has found a match. Aap doesn't find a match. Meherbani finds a match, and Hogi also finds a match. So the process is to take every word in the candidate and find out if it has a match in the one of the reference translation. That is the procedure. So now candidate 2 is aapki, aapki, aapki meherbani. 3 aapkis and then 1 meherbani. So the matching unigrams is 4 in this case. Okay, matching unigrams is 4. The first word aapki, does it match? Yes. Second word, yes. Third word, yes. Fourth word, yes. So the unigram precision is 100%, 4 by 4. So it seems to create an impression that the translation is extremely good vocabulary wise. Okay. So the metric can be fooled by repeating the word from the reference translation many times. So then what should we do? We have to correct this error. So we do what is called modified precision. Modified precision is we obtain the clipped count with respect to the n-gram. That formula is minimum of count, comma, max of reference count. So if we take the reference translation, आपकी बड़ी मेहरबानी होगी, and candidate 2 is आपकी 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 मेहरबानी, then you take the first word, आपकी. Okay. So आपकी, there are 3 matches for आपकी. Okay. Whereas in the reference count, the word आपकी appears only once. So the flip count will be minimum of 3, 1, which is 1. Okay. And meherbani is again 1, 1, which is 1. And that gets corrected. Yeah. Yeah. So candidate 2, I go position wise. Okay. In the first position, I have Apki, which has a match in the reference translation. Second also, third also. And similarly. Huh? No, you will match the candidate with reference. I can't hear you properly. Mm. No, no, no. It's a set. You look up on the words as set. Of course, the duplicates remain. No, the order is not important. Yeah. Mm. So when we take clipped count is minimum of count, comma max of reference count. Uh, here, aapki matches 3 times. Okay, with the same word matches 3 times, but the word as such appears only once in the reference count. Okay, and then we will take the flip count in the form of minimum of these 2 quantities. Then the correction is achieved. So what will be the unigram precision now, it will be 2 by 4, which is equal to 0.5, right? And the unigram precision in case of correct translation is higher for this. So therefore, that translation is better. आप बड़ी मेहरबानी होगी and आपकी मेहरबानी. Between them, which one is a better translation? Native speakers of Hindi. I mean, you might argue and come back say that आपकी मेहरबानी is very good. Okay, there is a lot of emphasis on आपकी, but that takes us into pragmatics. And there is clearly a point there. Okay. So unigram precision is 0.75 for the first one, and corrected unigram precision is 0.5 for the second one. Okay. So then we get the core of the blue formula. The core of the blue formula is this: Pn, precision at n for n gram, is equal to this formula, which is essentially the number of times the candidate n grams match with the reference divided by the number of the n grams, okay, in the candidate transmission. Let me repeat this point. Let's note this, okay? So the denominator of the formula is the number of n grams in the candidate transmission, okay, not in the reference. If you take it in the reference translation, then the formula becomes a different formula. It's called Roos score. Okay. So the number of n grams in the candidate translation is the denominator. And in the numerator, you have number of n grams which are matched, which finds a match in the reference translation after clipping. Okay. And why there are two sigmas? The inner sigma is for the n grams in a sentence. The outer sigma is for all the sentences in the corpus. Okay. So two sigmas are for sentence and corpus. The denominator is also that way. Any question? This is a core of the blue formula. So now the question comes, I have computed P1, P2, P3 up to P4, typically up to P4. How do I combine them? Okay, we combine. Okay, I'll come to correlation later. There are other discussions, how to combine. No, I think I should go in the flow. Okay. So comparing human transmission and machine transmission precision. So that's very important. Any metric we propose in AI, we'll have to show its correlation with the human performance. So from the original blue paper, which is Papinani et al. In 2002, this is the correlation study. 127 source sentences were translated by 2 human translators and 3 empty systems. Translated sentences were evaluated against professional reference translations using modified n-gram precision. Okay, a modified n-gram precision means clipped count. Okay, so now let's look at this diagram, which is a very famous diagram. First, we have the x-axis. X-axis is 1, 2, 3, 4. They correspond to unigram, bigram, trigram, and quadrigram. Okay, so let's take unigram, and there we see a red bar, yellow bar, green bar, blue bar, and a sky blue bar. So red bar corresponds to human translation. H1 also corresponds to human translation. That is, yellow also corresponds to human translation. And then S3, S2, and S1 are the outputs of three machine translation systems. So the precision is plotted on the y-axis. And let's look at this figure. Now, precision, if there is an identical candidate translation, identical to the reference translation, then the precision score will be 100%. Okay, that's why the maximum value is 1. It cannot be more than 1, right? The denominator is the number of n-grams in the candidate translation. Okay, the total number of candidates in the n-grams in the candidate translation, and on top you have matching n-grams from the candidate translation, so the value cannot be more than 1. So what do we see? Let's look at the sky blue bar. It has the lowest precision, unigram precision, compared to every other system. So there are 2 human translations and 3 machine translation systems. Okay. So human translation is also compared against a reference translation. We assume the reference translation is from real expert. So it is interesting to note that the red bar has a precision of 0.65. What does it mean? The H2's translation has unigram precision of 0.65. Okay. The H1's performance is slightly lower, which is the yellow bar, and all the machines' performance is lower than human being. Right. So this is what is happening for the unigram. For bigram, we find that in general the precision value is lower, and trigram it is still lower. Quadrigram is much lower. Okay. So as n increases, then the n-gram precision value goes on reducing. Okay. Why so? Can this be explained? So one unigram mismatch gives rise to 2 bigram mismatches. One before, one later. Okay. And one unigram mismatch gives rise to how many trigram mismatch? 3? Right? 3. So this is this percolating effect. And therefore, as unigram value precision decreases, the bigram and trigram and quadrigram values also decrease quite drastically. Okay. So this particular diagram tries to establish correlation between human performance and machines performance. In particular, it tries to establish the fact that blue is a good metric considering the correlation with human performance. Yeah. So this is 2002 paper. Okay, now we know in our era of deep learning based machine translation, the number has to be much larger. 2000, 3000, 10,000 is also very common. Right? So this particular diagram comes from the paper itself and has been referred to many times to establish a correlation between, show the goodness of correlation between blue score and human performance. How does it show this? How does this diagram lead to that correlation? How will you go about establishing the correlation? Yeah, so this situation is somewhat strange. We are evaluating an evaluation measure, no? Isn't that a bit strange? We are evaluating an evaluation measure, okay? And the way we are evaluating an evaluation measure is by establishing correlation with human performance. Okay, so I'd leave it to you to understand that this bar chart, which is very famous, has remained in the field, is a good indication of correlation of human performance with our machine performance with respect to evaluation. And the reason for creating automatic metrics for evaluation is really scalability. How can you really test lots of machine translation output by human adequacy fluency scores? It takes a lot of time. So that's why we develop a evaluation measure, and that evaluation measure is very simple. It simply takes the unigram precision, bigram precision, trigram, quadrigram, and then combines them through some measure, which we'll see. Now there are more, complexities involved here. A point about the length of n-grams. 1 gram and 2 grams stress vocabulary match and lexical goodness. 3 and 4 and higher n-grams stress structural match or syntactic goodness. This is a very fundamental point, and one of the reasons why blue has withstood the test of time. So when you take unigram and bigram, it stresses the match of vocabulary. Unigram is understandable. You have matching of words. Why bigrams also stress vocabulary match? What are bigrams? Bigrams are two-word combinations. Okay, and we know that every language, the vocabulary consists not only of one words. Vocabulary also consists of 2 words, 3 words combinations. In fact, it is shown in a paper that about 40% of the vocabulary are what are called multi-words. Okay, multi-words are extremely important in NLP. Multi-words. So Anshul, you'll have to give this like multi-words. Multi-words are of two kinds. Compositional and non-compositional. Compositional meaning equal to meaning of parts. Combination of meaning of parts. These are called compositional multi-words. Non-compositional, meaning cannot be made out from the meanings of parts. So an example of this would be, this is my favorite example. White elephant. Okay. And an example of this would be strong opposition. Okay. So strong opposition, you can make out the meaning from the meaning of strong and opposition. Okay. The fort had to be surrendered. The fort could not be, no, the fort was well protected in spite of very strong opposition. Or, sorry, the bill was passed in spite of strong opposition. White elephant, can you make out the meaning from the parts? What is the meaning of white elephant? What is it? Something which is in your possession and is very difficult to maintain because of the cost. Okay, my old ambassador car is a white elephant. The story goes that the king of Thailand, whenever he wanted to punish somebody, he would give the white elephant to that person. You see white elephants only in Thailand. Okay, so he would give a white elephant to that person with the condition that nothing should happen to the white elephant. It should not fall sick. It should not go hungry. Nothing. And you have to arrange for the food of that white elephant, which is an enormous expenditure. Okay, so the term white elephant comes from that story. White elephant is a metaphorical usage. It means an object which cannot be maintained because of the large expense. So now the interesting thing is that every language has these kind of constructs, compositional and non-compositional multiwords, and it forms 40% of the vocabulary, and they should match. Okay. Now, these compositional multiwords are also called collocations. Collocations. Some words just go together. You cannot use a synonym to construct sentences there. Okay. So, for example, we say, I like to drink strong coffee. Now, the synonym of strong is, what are the synonyms of strong? Powerful is a good synonym. Okay, close word. In the evening, I like to drink powerful coffee or powerful tea. Doesn't sound good. So every language has these kind of collocations. They are called compositional multiwords and non-compositional multiwords. Anybody would like to suggest a non-compositional multiword from your mother tongue? From Ghoradim, yes. Ghoradim in Bengali. What does it mean? Yeah. Ghoradim literally means egg of a horse. So horses don't have eggs. Okay. So when we many times say Ghoradim pabe, that means you will not get anything. You'll just get a horse's egg, which means you'll not get anything. Something from Hindi, Tamil, iron pina. Oh, hard nut to crack. Hmm. What is the Kannada? Hmm. So it is interesting that all languages have this kind of constructs. Okay, collocations are more subtle. Okay, unless you are a native speaker of the language, you will not be able to make those collocations easily. And this is non-composition. You just have to store them in the dictionary. Now, question is, can large language models deal with multi-words? Okay, so try giving uh, wrong collocations to ChatGPT and see what it says. Okay, ask it. I would like to drink some powerful coffee. Do you see anything wrong in this sentence? It will come back and say that no, it should be strong coffee. Okay, so collocations, white elephant, these are easy to deal with in the era of large language models because of the huge amount of training that is done. and the very powerful probability model to capture the language model. So that's quite easy. Now, 3 and 4 are higher level n-grams, higher order n-grams. This match is required to do structural matching. Okay. Now, whenever languages are free word order, this kind of n-gram matching, where n is equal to 3 or 4, often gets into difficulty. Okay. Free word order languages can express the meaning in many different ways, and therefore you need many reference translations in free word order languages. So trigram, quadrigram will fail in case of free word order languages and give a misleading impression about BLEU score. So that is why BLEU score has been criticized very badly. There was a time when BLEU score was thought to be completely unsuitable for the free word order languages. Okay, then variations on BLEU score came. To deal with synonym, Meteor came. Okay, so to deal with free word order languages, there were other constructs introduced. Subwords, for example, were introduced. So we'll discuss those things later. Now recall. We discussed precision. Precision is the number of correct divided by the number of total number of n-grams. Recall. The case of candidate shorter than reference. Now you see this another interesting phenomenon appearing. Will BLEU be able to understand the quality of long sentences? This is the English sentence. The Hindi sentence is क्या BLEU लंबे वाक्य की गुणवत्ता को समझ पाएगा? Now, the candidate translation which is produced is just lambe vakya. Okay, so if you capture just 1 or 2 words from the reference translation, then you will get very high precision for all n-grams. And it will give an impression that your translation is very good. So the translation is good in parts, but it doesn't capture the whole meaning of the sentence. So the adequacy score would be very low. Now, I ate food. The reference translation is maine khana khaya, and the candidate output is maine khana khaya, where precision P1 is 1. When the candidate is longer than the reference, then reference 2 is maine bhojan kiya, and candidate 1 is maine khana bhojan kiya. Then again, we see that the metric has undesirable behavior. But let me come to the main point here. The main point is that the sentence length is an indicator of good match. So if the candidate translation's length is extremely different from reference translation, then we can be sure that the translation quality is suspect. So what was introduced is a correction factor. Just like clipping was a correction factor, brevity penalty was another correction factor. There is a multiplicative factor. Candidate translations that match reference translations in length must be ranked higher. Okay, that is the requirement. Now, if the candidate translation is very small, captures just 1 or 2 words from the reference translation, then it should be subjected to this correction. So candidate 1 for this sentence is lambe vakya. Candidate 2 is क्या BLEU lambe vakya की गुणवत्ता समझ पाएगा. So in both cases, you will get the precision as 100%. But the quality of translation is very different between the candidates. So what was done is that a brevity penalty factor was proposed. So if the candidate translation's length is more than the reference translation, then brevity penalty is equal to 1. Otherwise, it is e to the power 1 minus r by c. So when r is equal to c, this is e to the power 0, which is equal to 1. As c becomes smaller and smaller, then r by c it goes on increasing. It becomes more than 1. Then you will have this quantity as 1 by e to the power something. So this comes as a reducing factor for the precision value. So then what is the final blue core formula? This is the blue score formula. Blue score is equal to BP into e to the power sigma n equal to 1 to capital N, Wn log Pn. So Pn is the core formula on the right hand side. Okay, Pn, precision of unigrams, bigrams, etc. Pn. Brevity penalty is a multiplying factor. Now, what is this e to the power? See, it is e to the power n equal to 1 to n Wn log Pn, which is equal to log p to the power n Wn. Right? This can be written as log p to the Pn to the power Wn. And summation of logs is log of products. Okay. And e to the power log is giving you the product itself. Okay. So, so this is equivalent to e to the power right is equivalent to this, which will be equal to now what is Wn? Wn is the weightage given to the n-gram precision. Okay, so if we and this Wn should sum to 1. Okay, now if we make Wn is equal to 1 by 4, okay, and n goes from 1 to 4, let's say 1 to 4, then this will be fourth root of P1, P2, P3, P4, which is nothing but the geometric mean of the 4 precision. Okay, and geometric mean is between harmonic mean and arithmetic mean. Arithmetic mean gives importance to highest value. Harmonic mean gives importance to the lowest value. Geometric mean is in between. Okay, so geometric mean has been found to be a good method of combining all n-gram precisions. Okay, so let's finish the story in the following way. The core of the formula is this. This is everything. Okay, the number of matches divided by number of n-grams in the candidate translation. If the candidate translation is very short in length, it will get credit which is not real. So that's why you introduce BP. So if you multiply this by BP, Okay, then it will have a reducing influence on this geometric mean. No? If the candidate translation is shorter in length than reference translation, there will be a reducing factor. So the core, which is a geometric mean, if all the weightages are same, otherwise there is some kind of weightage given to different precisions. It depends on which precision, where you are giving more importance, syntax or vocabulary. If you say that I do not care if the sentence is well formed or not, the meaning should be conveyed. Okay, then give low weightage to trigram and quadrigram, but all because all the WN should sum to 1. Okay, reduce the importance of quadrigram and trigram. But if you say that no, I'm very interested in fluency, I want the sentence to be really well formed, and I do not care about the meaning, that will not happen typically. Then give high weightage to W3, P3, and P4. Okay, then this formula will be different. Okay, mark these small things carefully. These are the things which are asked in the quiz, midterm, and so on. Okay, to note whether you have carefully considered a concept from all points of view. Okay. And by the way, the next quiz will be the last Thursday of October. Okay, and this will be a completely multiple choice. Okay, so this is how the blue score is arrived at. And slowly from different considerations, it is derived. It's a very instructive exercise. Okay, I want automatic evaluation to be performed. I have the scalability problem. I do not have money to employ 100 people to look at all possible translation. Okay, and therefore I think of some kind of matching with the reference translation. Then I think of unigram to give importance to vocabulary, unigram, bigram, trigram, quadrigram to capture syntax. So it is not the case that the designer of the blue score was not aware of the language phenomena. Definitely, the designer of the blue score, Kishore Papineni and Steve, were careful to accommodate the language phenomena. Then came this interesting point of taking geometrically, not arithmetic, not harmonic, geometrically. Then if you have a very short output, short translation, it will get undue credit. This should be reduced by brevity penalty. Okay, and then you have this final score, which is in front of you. All the weightages should sum to 1, of course. So this is a very nice, simple exercise of arriving at a metric, considering language phenomena from different points of view. This is something we should appreciate and learn. Now, the question is, employing these large annotation teams, team of human beings, does it happen? It happens. Where does it happen? It happens in RLHF, in large language models. ChatGPT, the OpenAI as a company, employs 4,000, 5,000 what are called AI trainers. They have a lot of money, and they have therefore employed a big team, which gives continuous feedback to the large language model. If I do not have so much money, will have to think of some automatic mean. Then I have to consider the language phenomena, the properties of operators, geometric mean, arithmetic mean, and so on. Maths, probability, linguistic phenomena, all these will come into play. So this is an interesting exercise and very instructive. We should read the original paper by Papinini. It's there. Now, there is another score called Rouge, okay, which is used for summarization. I'll not spend time on this, but Rouge score is very much like blue score, except that the denominator is the number of n-grams in the reference translation, not in the candidate translation. So, sorry. So blue is called precision-oriented metric, whereas Rouge is called recall-oriented metric. Okay. So how many correct n-grams from the reference translation you have been able to retrieve? Okay, it's called recall-oriented. Now, if time permits, we will go into nitty-gritties of comparison of blue score with rouge score. What difference does it make if you have n-grams taken from the reference and added in the denominator? What difference does it make? So it's called recall-oriented score. It is used in summarization. Also, why is it appropriate for summarization, whereas blue is appropriate for machine translation? These are nice, subtle questions, and um, and you should, on your own, read up and think about them. This is called rouge score. There is what is called rouge L, rouge W, rouge S. Okay, all these I have given there. Now let's begin test of hypothesis. A very, very fundamental concept in whole of AI. And again, this is one of the concepts whose relevance has not changed from different generations of NLP, one generation to another generation. The relevance hasn't changed. First of all, I'd like to introduce a problem which I'm very fond of, and some of you are third year CS students. We have seen this example and quite a lot of these discussions covered last semester in CS215. But there is no harm looking at this once again because they have a lot of subtleties. So I first proposed a practical problem, nothing to do with NLP. This problem is from this very well-known probability book, Probability for Scientists and Engineers by Sheldon. Okay, I think this is there in the reference list. Sheldon. Sheldon and Ross, third edition. I don't remember the year. Yeah, a very famous book, and this example is from there. Now, why probability is inevitable? Okay, it shows why probability is inevitable. A situation which holds for natural language processing or language understanding. Okay, so now this is a problem. A bridge is being built. The weight it can tolerate has a distribution with mu equal to 400 and sigma equal to 40. So it's normally distributed, okay, and the mean is 400, standard deviation is 40. A car that goes on the bridge has a weight distribution given by mu equal to 3 and sigma equal to 0.3. That means the weight of the car is also normally distributed with mean equal to 3 and standard deviation equal to 0.3. We want the probability of damage to the bridge to be less than 0.1. How many cars can we allow to go on the bridge? That's a question which the city authorities have to answer. How many cars it will be safe to allow simultaneously to be on the bridge? Okay. Now, sorry. Now, the weight the bridge can tolerate has a distribution with mu equal to 400 and sigma equal to 40. So as you know, the probability parameters can be computed only from data. If data is not given, you cannot get the parameters of a probability distribution. You are told, of course, that this is normally distributed. If it is not normally distributed, then what will you do? You will have to resort to central limit theorem. I don't care if it is not normally distributed, but if the number of observations crosses a threshold, typically 30, then normal distribution is a good approximation for the underlying distribution. So that's called central limit theorem. Okay. So now the weight that a bridge can tolerate has a distribution. So what does the having distribution mean? It means that it varies from bridge to bridge. Okay. So the height of people has a distribution. My height is different from your height, a third person's height. So this means that means there is a variable which takes different values. And when does a variable become a random variable? Can somebody say? What is the difference between a variable and a random variable? Hmm? Function. Okay, in simpler terms, can't hear you. I can't hear you. Uniform distribution. Okay, well, so let's remain very informal and not extremely rigorous. Uh, a variable can take different values. And if we can associate a probability value with the values, if we can associate a probability with the values that the variable can take, then we'll call it a random variable. The definition is much more rigorous. Okay, we have to we are just introducing probability here to introduce the concept of random variable. Now, if I take any bridge and uh, try to find out what tolerance it has to tolerance to breakage, then the value will differ from bridge to bridge. Okay, right? From bridge to bridge. Now, notice that getting these values mu equal to 400 and sigma equal to 40 is non-trivial. First of all, you cannot take a bridge, break it, and then obtain the value. Okay, this will be very costly. So what is typically done these days, civil engineers, chemistry, physics, electrical engineers do, they do a lot of simulation, right? And from simulation studies, you get a uh, get a set of values under which the bridge will break, and that will be a distribution. We say that this will be normally distributed. That is also an inherent property. Okay. So now it is normally distributed, has mean of 400, sigma equal to 40, and the car that goes on the bridge, that also has a weight distribution. Every car has a different weight. And we were saying that this weight distribution also is normal with mean 3 and sigma 0.3. This is the situation now. Hmm? We want the probability of damage to the bridge to be less than 0.1. Let I would have actually omitted this sentence and just thrown the question. The question in front of the city authorities is how many cars can we allow on the bridge? Okay. And to answer this question, the question is very simple. The last question. A bridge has been built. How many cars can we allow to go on the bridge? That's a question anybody will understand. You don't need a statistician, probability theories, probability experts to understand that question. To answer that question, we have to dig deeper. Okay, we have to first propose that the distribution that the bridge can tolerate is normally distributed. The distribution of the car weight is again normally distributed with mean and standard deviation, which is found from data. Okay, and we want the probability of the damage to the bridge to be less than 0.1. Let's see, how to approach this problem. When does the bridge break? If the total weight on the bridge is greater than the tolerance weight. Hmm? Okay. So let's take a deterministic approach to answering this question. So the bridge will get damaged if 3n equal to 400. Where does 3 come from? 3 is the mean weight of the car. Okay, and the tolerance weight, the mean of the tolerance weight is 400. Then if I say 3n equal to 400, then n equal to 133. This is a possible answer. Okay, I will not allow more than or even close to 133 cars to be on the bridge because the car's mean weight is 3 and the mean tolerance weight is 400. Does it sound intuitive? It makes sense? What do you say? Do not be biased by probability and distribution. Isn't it a good approach? Most of the city authorities will do this. But the point is that and I would like to show you how all this is relevant to language. So car weight. Car weight is a line or is it a spread? It's a spread, no? Car weight is a spread. The tolerance weight, is it a line? It is also a spread. How can a spread talk to another spread? How, how can I aggregate the spread here and use it to negotiate with this spread? That is the question. Spread has to talk to spread. Okay, so this equation is a deterministic equation. 3n equal to 400, n into the mean is equal to mean tolerance of the bridge. Intuitive. Only thing is that it is not considering the spread. Okay, and if you do not consider the spread, what can happen? Let's see. So this was a point-wise, a point deterministic approach, but deterministic with bounds. Let's see. The strongest bridge, let's consider the best possible situation. The strongest bridge and the lightest car. Okay, so the bridge can withstand 440 as the tolerance weight because standard deviation is 40. Okay, 400 plus 40. And the car weight is 3 minus 0.3. Mean weight is 3 and standard deviation is 0.3. So 3 minus 0.3, 2.7. So the most liberal situation, but also most risky will be ceiling of 2.7 n equal to 440, where n equal to 163. Okay, by considering the bound. Then this will be a very happy situation for city authorities who are trying to make a lot of money from toll taxes. Okay, a lot of cars come onto the bridge, they pay toll, and the money comes into the city authorities. Kitty, very happy situation. And more than full utilization of the bridge. Only thing is that the bridge will break. Okay, and after some time, all this money will go in repair it. Whatever the most conservative situation, weakest bridge and the heaviest car. The bridge can withstand only 360 units of weight. And the car weight is maximum 3.3, 3 plus 0.3. Then the most conservative situation and the safest situation is this. Floor of 3.3 n equal to 360, where n comes out to be 109. Very safe. The bridge will not break. But the point is that it will not be utilized also. Capacity utilization will be low. So that's also now not a very happy situation for the city authorities. A facility must be used. Okay, so this will be a very safe situation. Only 109 cars will be allowed. The toll tax collection will be very low, but the bridge will survive. And 3n equal to 400 gave me 133. So we have three numbers. We have 133, we have 163, and we have 109. Notice that I cannot give any guarantee. I have no instrument in this approach to give the guarantee. With such and such probability, the bridge will break or will not break. You see the need for probability? So if you don't use probability, then you are away from reality. You do not consider this phenomenon that there is a spread. There is a spread. This spread you are not accounted for. Your approach is very ignored. Then if you want to play very safe, yes, but it will not be, the facility will not be used. If you want to go completely liberal, then it will be unsafe. And these are the trade-offs we have to consider. Right. So you get the setting, right? You understand this whole setting. So most liberal is 163 cars. Most conservative is 109 cars. What should be the actual number of cars to be allowed? This is an objective decision because finally the authorities have to bring out a notice. No more than n cars will be allowed on the bridge. So a precise number has to be allowed. How much is that? Now let's see the approach. As an administrator, I want to play very safe, no risk, then only 109 cars. Bridge will never break. I am safe. Point of view and priority, earning first, throughput first, efficiency first. I want to have maximum utilization of the bridge, maximum earning from toll, maximum movement across river, maximum economic activity, maximum interaction. People are very happy. Okay, then the bridge will very likely cross the tolerance limit. The bridge breaks, lives are lost, property damaged, people unhappy. Okay, so these are the two situations. Now, this is also related to COVID situation. Do not go out at all. Do not interact with anybody. Very safe. Will not get COVID. How to sustain? How to break the monotony? You'll have to eat also, right? Then how to get the sweet spot, the middle path? The answer is probability. Okay. So it's a multi-objective optimization problem. Many objectives have to be satisfied: safety, utilization of facility, earning, people satisfaction, and so on. It's a multi-objective optimization problem situation. So let's bring in probability. It is brought in the following way. The number of cars, let it be n. Okay, only up to n cars will be allowed. Each car's weight is normal with mean equal to 3 and standard deviation 0.3. Now we invoke central limit theorem. Central limit theorem I'd like to do in the class at some point of time. Now itself. And then you make use of these results. By central limit theorem, the sum of Gaussian random variables is Gaussian, with mean and variance being the sums of individual means and variance. Okay, so the sum of the Gaussian random variables is Gaussian, with mean and variance being the sums of individual means and variance. Very powerful result. This is the central limit theorem. So now total weight of n cars also follows a normal distribution, and the mean of this total n cars, the mean weight of the total n cars is 3n. You can sum the means and get the resultant mean of the Gaussian distribution. And the variance is equal to sum of variances. Okay. Now the variance is, the standard deviation was 0.3, the variance will be 0.3 square, which is 0.09. So the standard deviation of the resultant distribution will be 0.09n. Okay. So we have been able to get the total weight, the mean of the total weight of the cars and the standard deviation of the total weight of the car. We've been able to get these two. Yeah. Will it hold if they are not independent? Yeah, the sum of expectations is expectation of sums that requires independent. Ah, okay. Yeah. So this I'll have to verify. Has to win. So they're independent, like the cars' weights are independent of each other. So W tolerance looks like this. Uh, the bridge is damaged when W total is greater than W tolerance, or W total minus W tolerance should be greater than 0. Okay. And the guiding equation is this. What we want is this. Probability of W total minus W tolerance exceeding 0. Sorry, the probability of W total exceeding W tolerance, that probability should be greater than 0.1. Okay, if n cars are allowed on the bridge, right? Or we want the probability of W total to be less than W tolerance to be very high. Okay, 0.9. So this is the probabilistic formulation, and we'll come to that a little later. So our guiding equation is this. Okay, we'll develop this particular theme and then show how the probabilistic method is used to answer this question with a lot of guarantee and lot of good theoretical underpinning. Okay, so let me finish the class just emphasizing one point to you, which is that keep thinking about how a distribution interacts with another distribution. Okay, in the non-deterministic probability-based world, we cannot write clean equations. Okay, the equations that we are used to, deterministic equations. We have to talk about bounds and probability. Okay.